Hello everyone, and thank you very much for attending this session. My aim today is to discuss some of the ways in which ETAP can help with more accurate arc flash analysis, and so build confidence in the calculated results. To start off, let me introduce myself and my company. My name is Nick Bramhall, and I'm a Chartered Electrical Engineer and Power Systems Consultant at Safe Arc Solutions Limited in the UK. I have more than 15 years of industry experience and have worked for several multinational engineering companies, delivering engineering design, consultancy, and operations support. I've been using ETAP for more than a decade and now work full-time on power system and arc flash study work. Safe Arc Solutions are a power systems and electrical safety consultancy based in beautiful Scotland in the UK. Our focus is on electrical safety and compliance, including arc flash. We have a range of clients across sectors, including oil and gas, manufacturing, and marine. Today, I'd like to share one of our ongoing arc flash studies with you to illustrate the benefits of using ETAP for power systems modeling and arc flash analysis in compliance with the latest IEC and IEEE standards. For this particular project, an arc flash study had been completed in 2009 by a different consultancy, but our client was struggling to effectively address the findings of that study due to a lack of confidence in the results. High incident energies beyond that of personal protective equipment supplied had been determined, and consideration was being given to deferring crucial operations and maintenance activities because de-energization wasn't always practical. This would likely have an impact on safety and reliability of the electrical system moving forward. We were challenged to evaluate the existing study report and determine whether the results could be acted on as is, or whether the study should be updated, taking into account changes in the intervening years, both to the system itself and to the underlying standards. As an aside, it's worth noting here that the UK does not have an equivalent to the NFPA 70E requirement of formally revisiting an arc flash study at least every 5 years. But of course, it's considered good engineering practice to revisit any type of electrical study on a regular basis, especially if system parameters are changing. Our review of the 2009 arc flash study report identified a number of issues with the way that the results had been determined. But before we look at some of the issues, I feel it's important to understand how the IEEE 1584 method determines arc flash incident energy. That is, the heat energy at the worker's head and torso in the event that an arc flash should take place. The model for incident energy has been empirically derived based on actual arc flash testing in the laboratory setting. This has resulted in a model which can take various inputs like voltage, short circuit current, arcing time, and equipment configuration, and determine a predicted value for incident energy for a specific piece of electrical equipment. The methodology looks complex. There's a number of long equations involved, but it can be broken down into just a few simple parts, as we show here. Firstly, the driving force behind the arc is the voltage fault current available at that particular point within the network. Secondly, the arc forms within ionized air, which has more resistance than a voltage fault. Therefore, the arcing current is lower than the voltage fault by an amount determined by the arrangement of the equipment. For example, how wide the gap is between conductors. Thirdly, the arcing current causes upstream overcurrent protection to trip in a certain time and clear the fault. This is the arc duration. So the amount of time the arc lasts for, coupled with the current driving the arc, along with some parameters of the system like voltage, is used by the equations to determine the energy released by the arc. This can then be used to determine a couple of different values, which really are the key outputs of an IEEE 1584 study. Firstly, the severity of the arc flash incident can be determined by calculating that incident energy at the worker's head or torso. These are usually some small distance away from the arc itself, known as the working distance. The arcing energy felt at this distance away from the arc is the incident energy. Secondly, as the arcing energy spreads out away from the arc, it reduces. The point at which it drops to 1.2 calories per square centimeter is called the arc flash boundary. As a worker approaches equipment to complete an activity where there could be a risk of arc flash, they must don their PPE at or before the arc flash boundary. Now, ETAP has a validated implementation of the IEEE 1584 methodology built into its arc flash module. Not only that, but it can also draw from other ETAP modules, like short circuit analysis using ANSI or IEC standards, or the STAR module for overcurrent protection, to determine all the required inputs to an arc flash calculation. The factors I mentioned previously rely themselves on a number of other inputs and a detailed understanding of the power system. The available voltage fault current depends on a number of factors, including sources of fault current, like generators, grid connections, or directly connected induction motors. It's also affected by impedance from equipment like transformers and long cable runs. Different system configurations, for example, single or dual transformer feeds down to LV switchboards, can also drastically alter the short circuit currents within a network. The exact configuration of the switchgear and the location where an arc occurs influences the physical characteristics of the arc and the resistance of the ionized air. This affects how much the arcing fault current is reduced when compared to the bolted fault current. The overcurrent protection, whether that's a fuse, a relay, or some other form of tripping device, will be set up to protect the system from a variety of faults, not just short circuit. So it will act in a certain time, depending on its settings and characteristics, to clear the fault and extinguish the arc. The working distance depends on the type of activity and the layout of equipment. Typically, lower voltage equipment involves a closer working distance. So bearing those factors in mind, we reviewed the original study from 2009 and identified a number of issues with it. Firstly, short circuit data was inaccurate and out of date. It had not been determined using an up-to-date power systems model, even at the time. Instead, it had been based on extracts from older reports, read from time current curves, or had been estimated based on the maximum let-through current of the upstream transformer. As the bolted fault current has a significant impact on arcing current and therefore on trip times, changes to this value can have knock-on effects to the determination of incident energy. The second issue we identified was that overcurrent protection details were unknown or had been assumed, and of course any changes in the intervening years were not accounted for. As with the bolted fault current, inaccurate trip times can also lead to inaccuracies in the incident energy. I'll demonstrate how this can change with an example at the end of the presentation. Third issue was that limited system configurations had been identified and studied. Again, depending on the circumstances, differences in configuration, perhaps more or less generation, more or less largely directly connected motors, or parallel transformers, can all have a significant impact on the bolted fault current. They should be explored as part of a study and common configurations considered. In addition to this, the study had been completed according to the first edition of IEEE 1584, and so did not benefit from the increased inaccuracy afforded by the second edition, which was published more recently in 2018. In the years between the first and second editions of 1584, thousands more arc flash tests have been conducted, with the data from those used to refine the mathematical modeling of the arc and the resulting incident energy. An important difference is the introduction of more electrode configurations, which more accurately represent the different arrangements of conductors found in metal-enclosed switchgear, common to many industrial settings. The most significant change was the introduction of horizontal conductors in a box, which is abbreviated to HCB. These arrangements are the worst case for arc flash incident energy, as they direct the heat energy of the arc flash straight out towards the worker standing in front of the equipment. The updated methodology also refined the concept of arcing variance. In 2002, this was a simple percentage reduction. In 2018, there is a more sophisticated calculation which takes into account the arcing current in the electrode configuration. And a final change to mention is the introduction of an enclosure size correction factor, which allows for different enclosure sizes to be used and more accurately reflect actual equipment. So in order to address the issues we identified and generate a more accurate set of arc flash results, we proposed building a detailed model of the electrical distribution using ETAP 22. The client was able to supply detailed data to support this activity, including original databooks for the switchboards and a recently as-built protection setting schedule. This allowed us to determine things such as the overcurrent protection relay equipment and settings, including the CT ratios. The drawings provided allowed us to determine electrode configurations and enclosure sizes for much of the switchgear. The data provided allowed us to do more accurate modeling and configuration of direct online motors. So with a detailed model built, we could then take advantage of ETAP's various modules and features to run a suite of studies, including short circuit according to IEEE 60909, and checking protection coordination in the STAR module, before going on to then run the arc flash analysis itself. I have a couple of examples of the more accurate modelling completed as part of undertaking the study in accordance with the 2018 edition of 1584. First up here is the main 11 kV switchboard. This is metal enclosed switchgear with withdrawable vacuum circuit breakers as shown on the right. The operations and maintenance manual for this equipment shows the arrangement of the circuit breaker spouts, which is one of the areas where an arc flash could occur. A misplaced metal tool or a loose panel could drop behind the truck as it is wrapped back in and cause an arc flash. As the spouts are aligned horizontally, we select the HCB configuration to account for this worst case scenario. The manual also gives some dimensions for the circuit breaker compartment and an idea of the gap between the electrodes. This allows us to put in key IEEE 1584 data for the switchboard as we show here. We can now take a look over at the calculated results used in this data and the differences between the two studies. For this switchboard, there was little difference between the short circuit calculations. However, the figure we have determined is more accurate as it uses better models of electrical machines, such as the generators and motors. However, the biggest impact on the results was applying the 1584-2018 methodology and the HCB electrode configuration. This results in the calculated incident energy almost doubling compared to the previous study and highlights the high potential severity of an arc flash at this particular switchboard. A second example to show you is that of the 415-volt MCCs, motor control centers, which are used to supply the majority of consumers on the installation. We were able to model these in greater detail thanks to the data provided. This included separately modeling the power and feeder sections, which have very different characteristics. The power section, which includes the incomers and bus coupler, were modeled as large air circuit breaker cubicles. For the incomers, we used the upstream backup protection at the 11 kV switchboard to provide that overcurrent protection. We extracted compartment sizing information from the general arrangement drawings and were able to determine that a VCBB configuration would be appropriate. The construction of these air circuit breakers means that there is a barrier at the rear, which can help dissipate some of the arcing energy. The feeders were modeled as much smaller motor control cubicles. Each MCC has a range of cubicle sizes from 1U upwards. We chose the smallest, 1U, to determine the arc flash incident energy. The smaller enclosures focus the arcing energy and so generally present a worse case. For the feeders, we determined there was sufficient segregation to allow the local incomer protection to be used here. Again, accurate enclosure dimensions were extracted from drawings and VCBB was determined to be the appropriate electrode configuration. We used ETAP's enclosure editor to easily set up these two different configurations for the switchboard and evaluate both sets of results at the same time. Here you can see how the incomer and feeder have been modeled within the enclosure editor. The incomer has been selected as the protected device for the feeder evaluation, so that the local protection acts to clear an arcing fault here. Doing this provides a greater level of understanding of arc flash severity depending on the location of activities on the switchboard. It is much more likely that activities will take place on the feeders than on the incomers, which might only be isolated for maintenance on something like a 4-yearly basis. Applying the incomer arc flash severity across the whole of the switchboard would mean that more onerous mitigation measures are required at the feeders than in reality. If we now look at the comparison of results for the LVMCC, you'll see there are a few differences. A more accurate determination of the short circuit current has been made using the ETAP model, including accounting for things like cable impedances between the transformer and the switchboard. Contribution from local motors, though of less significance at LV than at HV, were also included using ETAP's lump load. As noted, both the enclosure size and electrode configurations were changed to better represent this equipment. As a result of the various changes, there is a difference in incident energy for both the incomers and feeders. we see that the incident energy at the incomer has decreased from 78 to 51 calories per square centimetre, whilst the feeder incident energy has actually increased from 22 to 32 calories per square centimetre. Now, this slide shows a summary of the results for a selection of key switchboards. We were able to accurately determine the potential arc flash incident energies for a number of different operating scenarios that reflected the network as it is configured and operated today. The table shows a comparison for one of the operating scenarios that was also studied in 2009. We see a comparison of incident energies and a note of the dominant factor in the change. For the high voltage switchboard, I mentioned that the use of the HCB configuration was the dominant factor. At the 3.3 kV switchboard, there was little change in incident energy. This switchboard remained as a VCB type, but the contribution from connected motors was refined, resulting in a slight reduction in incident energy. The dominant factor at the LV-MCC incomers was a reduction in tripping times, found thanks to changes in protection settings that had not previously been captured. And finally, the feeder results were most affected by the use of the smaller enclosure size, which, as I say, focuses the arc flash energy and causes an increase, as we see here. And it's worth noting that when updating your study results from 2002 to the 2018 version of 1584, the results don't just go one way. There can be increases and there can be decreases, as we see in this case study. The relationships between short circuit, equipment configuration, and overcurrent tripping times really are best explored through ETAP's arc flash features. So to summarize, at the end of this process, we now have been able to provide our client with a highly accurate model of their power system built in ETAP using those latest features. This has incorporated detailed data provided by the client, and so cables, loads, and protection all closely reflect the actual system itself. We've also input into the model the latest protection settings based on an as-building exercise recently carried out. With that ETAP model up to date, we were then able to run arc flash analysis and complete this according to the latest version of 1584, taking advantages of the increases in accuracy afforded by this methodology. And overall, taking that all together, this gave us a much higher level of confidence in this particular set of results, even though we saw both increases and decreases in incident energy compared to that previous study. We now have a much stronger basis from which to do further study work and identify meaningful changes that can reduce incident energies and hopefully improve safety for personnel and equipment. As a brief example of the usefulness of an accurate model, we have now been engaged by the client to provide a full review of their protection settings. The arc flash analysis we completed highlighted long tripping times for many feeders, which is resulting in elevated levels of incident energy. It's important when doing a review of this kind that the changes to settings avoid compromising existing discrimination. And so this is another exercise which is made much easier now that we have a model built in ETAP. This slide is going to show you a couple of time current characteristic charts that we've put together using ETAP. In the middle, we see the protection as it is set today. This is the upstream and incomer protection to another of the 415-volt switchboards, similar to that we discussed earlier. We see that the instantaneous pickup is set quite high at nearly 15 times the rated current. With the arcing current at about 8 times the rated current, the relay responds fairly slowly, and we see a trip time of some 1.2 seconds. ETAP can automatically plot the arcing current on the TCC by selecting the options shown in the pane on the left. This slow trip time results in a high incident energy of some 44 calories per square centimetre. If we can reduce the instantaneous pickup to below the arcing current and still maintain coordination with the downstream protection, then there's a chance to really reduce the incident energy. In the TCC now on the right, we see that the pickup has been reduced to 6.5 times. The relay now trips instantaneously when an arc occurs, and so the clearance time is 0.06 seconds, far quicker than it was before. This makes a big difference to the incident energy, dropping it right down to 3 calories per square centimetre, a much less severe incident. Of course, other factors such as transformer inrush and downstream protection must also be considered when adjusting protection settings. This is just the first step in arc flash mitigation. Having invested the time in data gathering and constructing an accurate model, the client can now benefit from this and make decisions based on a much clearer understanding of the situation and the impact that any changes can make. Decisions can be made around arc flash mitigation, and the improvements can be demonstrated using ETAP quickly and accurately. Our intention is that this leads to a safer operating environment. So I'd just like to say thank you very much for your attention today. I look forward to discussing any questions or comments you might have during the panel session that's coming up a bit later on.